Okay, so let's look at a few of the forces that we're going to be using. The first one is the weight, and that is a force that you cannot escape if you're on Earth because the Earth is pulling on you. So the Earth produces a force that we are going to denote by W, and that is a weight. Mass and weight are not the same thing. The mass is how much stuff you have, and the weight is how hard the Earth is pulling on you. So the mass is also a quantity that describes the inertia. So the tendency of an object to resist being accelerated. Weight is the gravitational force exerted on an object by a planet, in particular by Earth. Typically, the weight is equal to mass times gravity. For instance, a person that has a mass of 70 kilograms, right? And then so the weight of that person is 70 kilograms times 9.8 meters per second square, right? Per second square. So that is equal to what? Let me just do it quickly here. So it's 70 times 9.8. That is 686 newtons. So a person that weighs that has a mass of 70 kilograms, the weight is 686 newtons. You can use different units for weights, either newtons or pounds. Those are units of force. 1 kilogram is equivalent to 220 pounds if G is 9.8. So that's only on Earth or in any other planet that has the same gravity. And 1 pound is about half a kilo, which is 454 grams. But remember, pounds are units of force, not mass, and kilograms are units of mass. So there is a property that your weight changes depending on how you're moving, the force that you feel, and that is the apparent weight. So why does that happen? Well, imagine that you are on an elevator and the elevator is moving up. So then if you draw a free body diagram for you, then you would have that the forces are the normal and the weight. So now there is a net force going up because you're accelerating. So remember, F net is equal to mass times acceleration. So the normal is actually greater than the weight. So and the force, if you put a balance here, so this normal force is actually the force that you would measure as your weight. So when an accelerator is, an elevator is accelerating, your apparent weight is going to be your weight plus mass times acceleration, which is the normal. So you're going to feel like you're heavier. In the same sense, if you're accelerating down, you're going to feel like you're lighter. If you're falling, then you don't feel any weight. There's no weight, and that is a sensation of weightlessness. And if you've done this free fall in amusement parks, then you'll notice that. So astronauts, when they are on the space station, for instance, they are in constant free fall. The space station is free falling on Earth to Earth, so they don't feel any weight. That's why they can float freely inside the station. Quick question here. We have a tilted coordinate system, and so we would like to know the coordinates of this of the weight here. So and this is a very important exercise that you need to be very good at. What are the coordinates? Wx is W cosine theta, sine theta, minus, minus. Which one is the right one? Just take a minute and think about this carefully. Alright, if you look at this, if you saw this, then you would know that your weight is this here. So this is theta. So this is the y component. So this is wy. So that is the adjacent, right? So that is the adjacent. So this one is w cosine theta. And so and this one here, that is the the x component, right? So that is wx, and that is w sine theta, because that is the opposite. So now they are both negative, so you get those negative signs there because they are both pointing down in this coordinate system. Normal forces. Normal forces is the force that a surface exerts on an object, and it always pushes perpendicular to the surface. For instance, here we have a table, the book on the table. So the table exerts a force up on the book, and that force is the normal force. If the book is not moving, that normal force should be enough to cancel, both the weight of the book and the extra force, the push of the hands. So basically the normal force increases depending on the force on the book. We can do this problem here. So we have a book that is 1.2 kilograms on a table, and the book is pressed down by the hand. The force is 15 newtons. What is the normal force from the table on the book? So we write Newton's equation. We only need the y-axis equation because there's nothing happening. So if you draw your free body, your coordinate system here, this is your y, this is your x. There's nothing happening in the x-axis, so there's nothing here in this x-axis, so you don't need to worry about that equation. So you write the forces in y is equal to the normal plus the weight plus the y component, which is n minus w plus f, right? So this here, and that is equal to the mass times acceleration, but the book is not moving, so that's equal to 0. So then I can find the normal force from here. So first I need to find the weight. Remember, the weight is mass times gravity, is 1.2 times 9.8. That gives me 12 newtons. That is the force from the earth on the book. That is the gravitational pull. And then there is an extra force from the hand that is pushing. So that is 15 newtons. So I have the hand force and the weight. So that gives me 27 newtons. That is a normal force. This 27 newtons is the force from the table on the book, and that is the normal force. In many problems, you're going to have cases in which the normal force doesn't point up. For instance, here, if you have an inclined plane, the normal force points at an angle. If you have an object that is being pressed against the wall, the normal force would be here. If you have a ceiling here and then you have an object and the object is being pressed against the ceiling, then the normal force is going to point down. So you need to be careful, and you need to know how the normal force points when you solve this problem. So typically you want to, here, for instance, in the inclined plane, you want to be able to draw all the forces and make sure you have the normal force pointing in the right direction so you can write the proper equations. Here is a simple example. You have a box that is sitting on the floor of an elevator. The elevator is moving upwards. The magnitude of the normal force is what? Is greater than mg, equals to mg, less than mg, equals to 0, or not enough information. Just take a minute to answer this and then come back to the video. So if you did this, then you would know that you have a normal force, and then you have the weight, and then we can write that the normal force minus the weight, that's equal to mass times acceleration. Now the acceleration is positive if I choose my coordinate system in this way, so therefore the normal force is equal to mass times acceleration plus the weight, so therefore the normal force is greater than the weight, and this is the right answer. Friction. Finally, we're going to talk about friction, and friction is an important force in nature. So there's two types of friction. There's a static friction and kinetic friction. A static friction is a friction that would be there if the object is not moving. Kinetic friction is the friction that would be there if the object is moving, either accelerating or at constant speed. Let's talk about static friction first. So the static friction increases with the push here. So she's pushing this box. The box has, what are the forces acting there? Well, there's the weight, the push, the static friction, and the normal force. As she pushes more and more, the static friction increases. Eventually, if she keeps pushing, she's gonna be able to move the box. At that point, the static friction, right before the box moves, the static friction reaches a maximum. That maximum is equal to a number that we call mu s, which is the coefficient of the static friction times the normal force. This is only true at the point before just the box starts to move. So the static friction, this is the maximum static friction that you reach just before you start to move. So she's pushing, and then you get a start. Let's look at the sequence here. She starts pushing and increasing the force, right? As she increases the force, then the static friction increases with the push, so as to keep the box at rest. Eventually, she's going to be able to push hard enough to move the box. At that point, just before the box moves, you have reached the point of maximum static friction, and at that point, you have that equation there. It's a very simple concept, but one that might be confusing. So the other type of friction that we need to worry about is kinetic friction, and kinetic friction is always equal to a friction coefficient times the normal. So once the box is moving, so the friction coefficient is going to be just one force, and that is equal to this. So it's equal to the friction coefficient times normal. So that friction, there is another type of friction, which is a rolling friction, which is equal to rolling friction coefficient times the normal. So here are tables for friction forces. So the friction coefficients that I mentioned about, they depend on the surfaces that are in contact. For instance, if you have rubber on concrete, like in cars, the static friction coefficient is 1, the kinetic friction coefficient is 0.8, and the rolling friction coefficient is 0.02. If you have steel on steel, right, dry, then this is 0.8, 0.6, and 0.002. If you have steel, look at this, this is very small. So steel on steel lubricated, then this is 0.1, 0.05, and this is very small, you don't even count. Wood on wood, then you have 0.5, 0.2. Wood on snow, you have 0.01, 0.06, and ice on ice is very small. So those are friction forces those are kinetic friction coefficients. If you need to use any of these in the exam, I'll give you this table for you to use the numbers. So then to summarize, we have the static friction coefficient, which increases with the force that is being applied up to a maximum. That maximum is equal to the static friction coefficient times the normal. Then we have the kinetic friction coefficient that is always equal to the kinetic friction coefficient times the normal. And then we have the rolling friction coefficient, which is always equal to, the rolling friction, which is always equal to the rolling friction coefficient times the normal. So those are the three forces that we need to work with. And finally, we have the drag. And the drag is just the force, the resistance from the Earth when you're moving on Earth. And it's typically proportional to the velocity squared. But one property of drag is that objects that are moving on the objects that are falling, they will reach what is called a terminal speed. So if you have a skydiver that jumps, it's not going to be accelerating forever. Eventually it's going to reach what is called the terminal speed, and that is when the weight cancels the drag. When you have those situations, then you get terminal speed.